Okay. So the last conic section that we need to discuss is that of the hyperbola. All right, so you can take a look at the geometry of what I'm talking about when I say a hyperbola really quickly. And then what I've done is, so that I just went ahead and took a snapshot of my notes so that you can see that I can read this quickly and you'll have reference to it. So what is the definition of a hyperbola? Well, it's the set of all points in a plane, right, for which, and we'll make sense of this in a second, for which what? For which the absolute value of the difference, now meaning subtraction, right, of the difference between the distances, so we're subtracting distances, is from distances from two distinct fixed points is constant. So notice, I'm looking here, for example. So notice that the focal points for hyperbolas are behind the vertices, right? So here's the vertice and here's the focal point. So notice that it's behind the vertices. You could say it. Look, you could say it's opening. It always opens towards the focal point. Same with parabolas. It always opens towards the focal points. Now, to say that this particular point is on this hyperbola, well, you take the two distances, the distance from focus 1 and focus 2, and then the subtraction, the difference between the two distances is always constant, right? So if the particle moves up here, the distances change, but when you subtract them, it will still be the same. Okay, now the absolute value, meaning so that way we're always dealing with positive numbers here, and that's actually equal to 2a. Sorry that was a little bit cluttered. So 2a. So let's discuss, just like with an ellipse, let's discuss what are we saying when we say a, what are we saying when we say b and c. So the distance, let's start with the distance from my apologies. So this is a little bit different than, yeah, my apologies. It's just how my eyesight's not that great. So I thought they used a different letter. So right now I'm looking at a focal point in the center of the hyperbola, right? That labeling a vertex has a little line to it that messed me up for just a second. So my apologies. No. So the distance from focal point to center of the hyperbola is what we call C. Now the distance from the center to the vertex is what we call A. Now the B in this case is, you'll have to kind of follow me down here. So there's two different axes that we'll discuss in just a second, but I'll kind of make sense of this distance B in just a second as I start to read along. So what do we got? So we got two foci, two fixed points. The vertices, the points on the hyperbola connected by the line through the focal points. Now, in other words, notice there's some line that travels through the focal points as well as the center. That line is what we call the transverse axis. All right. Now, the center of your hyperbola is always the midpoint of, so this is the transverse axis right here. So the center point of that transverse axis is the center of your hyperbola. Okay. So now the other axis that you don't quite see from this graph is what we call the conjugate axis. And again, it's just a line segment running perpendicular to, in this case, running perpendicular to the transverse axis. So I think a lot of this will become more apparent as we start to do some of these problems. But look, let's do this. Can you tell me the difference between these two equations and the equation from the previous video discussing the ellipse? Because, man, they look similar, right? Do you see the difference? Well, we have a minus symbol instead of a plus symbol. So that's what tells you that you're dealing with a hyperbola and not an ellipse. One of them is negative, or in other words, you have a minus symbol. So now the last bit of information that will become more relevant in just a second is I have focal points, I have vertices, I have center. I need a way of describing the relationship, and this is that relationship that I'll write on the next page. So again, notice the difference between this and an ellipse. C squared is equal to A squared plus B squared. Okay, so that's that relationship between those distances. Ready? So what we're going to do, we'll come back to this little theorem about the asymptotes in just a second, but what we're going to do is we're going to sketch the graph of the hyperbola. Okay, now, can you agree with me that with an untrained eye, if I wrote 4x squared minus y squared equals 16, for an untrained eye, it would be hard to tell that that's actually a hyperbola. But with a little bit of manipulation, if you just divide everything by 16, right? Now, why did I choose 16? Because I want the right side to equal 1. So dividing everything by 16 can move us to standard form. And now it's very easy to spot that, oh, okay, this is actually a hyperbola. So, okay, well, let's proceed. Let's actually go ahead and now that we're in standard form, let's identify the vertices, let's identify the focal point, all that stuff. So let's start with the fact that A squared in this case, B squared in this case. Now, I used a informal way of thinking about, I'm going to kind of go back for just a second. So I used an informal way when I was discussing if I was talking to my 11-year-old, Sebastian, how do I know which one is A, which one is B, right? In other words, how do I know, is it the 4 that's the A, or is it the 16 that's the A, all right? A squared. So in this case, what I said is, when dealing with an ellipse, I said, okay, you have two denominators. And I posed the question, which one is larger? And then, so for example, if you had a 4 here and a 16 here, if you told me, hey, the 16 is larger, then I would say, okay, is the 16 under the y or is it under the x? Remember that conversation in the previous video. So it's not quite the same when you're dealing with hyperbolas. You don't get to really ask the same question. It's a better question, or if you, let me kind of put it this way. And I'm trying to mix formal and informal, but I'm not doing too good of a job here. So how about I say, which one is the positive? Is the x the positive or the y the positive, right? Will you agree with me? In this case, x is positive, and since we have minus y, k squared over b squared, the y would be negative. So if your x variable is the positive one, then your hyperbola is going to run horizontally, meaning the transverse axis runs horizontally. Now, if your y is the positive, then your transverse axis is running vertically, and your hyperbola will look like the following. So notice that the A is always under the positive term, right? A is always under the positive term. So that would be the informal way of thinking about it. So in this case, let's you and I agree that the x is the positive term and the y is the negative term. So that would mean the A is again under the positive term. So in this case, A squared is equal to 4, and B squared is equal to 16. All right, well, that would mean if A squared is equal to 4, that A is going to be equal to plus or minus 2, and B is going to be equal to plus or minus 4. Okay, so far so good. So now since we're trying to sketch a graph, and we're not going to quite sketch it, but let's just establish that I don't see an HK in this version of my equation of the hyperbola. In other words, H is 0, K is 0. So I know that I know that the center of my hyperbola is at the origin, right? So notice here's the graph that we're dealing with. Notice that the center of the hyperbola is at the origin. So that makes things nice. Now, from the center, I'm going to travel, since notice the way I knew it would be drawn, the hyperbola would be drawn as such because the x is the positive variable. That means the transverse axis runs horizontally, right? The transverse axis runs horizontally because the x is positive. Okay, now, in this case, if I start at the center, 0, 0, if I travel 2 to the right, 2 to the left, I would get to my vertices. So the vertices would be equal to, well, we got to start at 0, 0, right? So the vertices are going to be, I got to go from 0, 0, I'll go 2 to the left, 2 to the right, so negative 2, 0, and positive 2, 0. Those are my vertices. I know those, I have 2 points on my graph so far. Now, likewise, we're not asked about the endpoints of the conjugate axis, but I'll show you why that's useful if you want to graph it. So the next thing, the thing that I don't have, and I wasn't even asked to find it, but since it's one of the few problems we'll do here for the hyperbola, the focal point. Well, don't you agree with me? Before I can find the focal point, right? I know it's going to be over here somewhere. If you're looking at my picture down here, I know my focal points are going to be over here, but to find it, I need to know C. So that's why you need this formula: C squared is equal to A squared plus B squared. All right. Well, so C squared is equal to A squared plus B squared. So that would mean C squared. I know A squared. I know B squared. So plugging in 4 for A squared, plugging in 16 for B squared, I know that C squared is going to be equal to 20. That means C is going to be equal to plus or minus the square root of 20, right? Or 2 square roots of 5. So I know I'm back at the center. I need to go the square root of 20 to the right. I need to go to the square root of 20 to the left, and that will get me to my focal points, okay? So you can write that. It's going to be 0, square root of, so square root of 20, 0, negative square root of 20, 0. These are going to be your focal points. Okay. Now, the question is, how do I graph a hyperbola if all I have is 2 points, right? Don't you agree with me? All I have is this dot and this dot. How do I then graph the hyperbola? Well, what I was talking about it with B. So the way this works is we're going to, so let's go back to the center. And don't you agree with me that B squared is 16? So that means B is equal to plus or minus 4, right? So if I'm at the center, I need to go up 4, then down 4. So that gets me to here. That gets me to here. So from the center, go plus 4, go up 4, go down 4. Now, those are not part of the hyperbola, but they are going to be helpful with graphing the hyperbola. So at this stage, to graph hyperbola is not always easy, but this is my conjugate axis. All right. So what I'm going to do is you would form a rectangle using the information that I've produced for you. And then notice that there's these asymptotes of the hyperbola, these dotted lines. So what without elaboration, right? I don't have time to elaborate on how we come up with these formulas for the asymptotes. But what I'm about to do is these asymptotes that I have on my graph right now, I'm about to show you the equations for those asymptotes. So if you follow me up here, so here and here, these are the equations for the asymptotes. It appears that my I must have moved things when I was my palm. All right, so these are the equations for the asymptotes. Y equals k minus a over b times x minus h, and y equals k minus b over a, x minus h. Okay, so you can use, and I'm going to wrap this up, you can use these asymptotes along with these vertices to sketch a decent hyperbola, okay, if you had to go at it by hand. All right. So I want to discuss mostly the rest of this section is definitional. Then I have one more little application I'll show you with hyperbolas. So if you want to discuss the eccentricity, first off, let's note the definition. So E is equal to C over A. And the idea is, since, if you recall, I had that equation, C squared is equal to A squared plus B squared. Don't you agree with me that that C is always going to be greater than A? Does that make sense? So C is always going to be greater than A, just from that little definition there. So that it just follows that the eccentricity is always going to be greater than 1. Okay? And I have two different pictures here. So if you have an eccentricity that's close to 1, then you can see how narrow your hyperbola is. If you have an eccentricity that's very large, like a large e-value, again, you can kind of see how that affects the eccentricity of your hyperbola. All right, so those were just definitional. Now let's actually do something that matters. So this, so we have what we're going to do is, this problem is what we call a hyperbolic detection system. And I told you that although these equations are old, right? They are the study of conic sections is quite antiquated, but the applications are not. So this technique was actually developed in World War II. And let me kind of read the question. So it says we got 2 microphones. So we have 2 microphones that are 1 mile apart. Okay, with me? So we have 2 microphones. Let's say it's World War II. We have 2 microphones that are 2 miles apart from or 1 mile apart from each other, and they both record an explosion. All right, an explosion happens. Now, it'd be really nice to pinpoint where that explosion occurred, which we will not be able to, but I will elaborate in just a second. But this is what we can do. Now, since we own both microphones, we record the explosion. We know the distance between the microphones, and we also know that microphone A received the sound 2 seconds before microphone B. Now, the question is quite misleading. It says, where is the explosion? But let me see if I can, let's see if you and I can agree on some things. So we know that sound travels at 1,100 feet per second, right? We also know that the microphones are 1 mile apart. Now, if I have sound in feet per second, then I don't want to use distance in miles, right? We want to keep the same units. So if I have sound in feet per second, then I want distance in feet. So the mics are 1 mile apart, meaning they're 5,280 feet apart. All right. So we also know that microphone A receives the sound 2 seconds before microphone B. Now, so every second that goes by, right? So we have 1 second, then 2 seconds. Every second that goes by, sound we will assume travels at 1,100 feet per second. So in 2 seconds, the sound would have traveled 2,200 feet, right? So in 2 seconds, at 1,100 feet per second, would be 2,200 feet. All right, now what does that mean? Well, let's see if we can start to get a graph going here. So notice that we can center our hyperbola at the origin, right? There's no, since we're only dealing with 2 microphones, this is simple enough. And let's start to piece together some information here. Okay, so we need A, we need B, we need C. and we need an equation. So let's start with 2c. Now, what do I mean by 2c? Let me show you. So remember, c is the distance from the center to the focal point. That is c. So in this case, we'll let microphone A be one focal point. We'll let microphone B be the other focal point. And it doesn't take a lot of analytic ability to understand that if microphone A received the sound before microphone B, then the explosion is going to have occurred on the right branch of our hyperbola, right? I mean, there is a left branch, but if microphone A receives the signal before microphone B, then that tells me that it's going to occur on the right branch of the hyperbola. Now, what I was saying just a second ago was, since the distance from one focal point to center is c, that would mean 2c is the distance from focal point to focal point. I'll say that one more time. The distance from center to focal point, we'll call that c. So what is 2c? Double c. Well, that would be the distance from focal point to focal point. And what is the distance from focal point to focal point? Well, aren't the microphones 1 mile apart? So in that case, if that's the case, then 2c has to be equal to 1 mile, 5,280 feet. Therefore, c is equal to 2,640 feet. With me so far? So get back to the center, go 2,640 feet to the right, 2,640 feet to the left, and there would be your focal points. Okay, now, what about the vertex? Well, again, we got to go back to the part where it says microphone A receives the sound 2 seconds before microphone B. So microphone A receives the sound 2 seconds before microphone B, and I know that sound travels at 1,100 feet per second. So, in other words, we know that 2A, or let's just say we have A is the distance from center to vertex, and then 2A would be the distance from what? Let me draw this other hyperbolic branch that we're not going to use. Let me just see if I'll do my best here. So don't you agree with me that if the distance from center to vertex is A, then 2A would be the distance from vertex to vertex? Do you agree with me there? Okay, let's see if you do. So vertex is A. Over here would be another vertex. So the distance from vertex to vertex would be 2A. So how do we put that to use? Well, 2A should equal what? Well, if microphone A received the signal 2 seconds, how does 2 seconds before microphone B, then we can use that, since 2 times 1,100 is 2,200 feet, that tells us the distance between our vertices. So from vertice to vertice, 2A is going to be 2,200 feet. That helps me because now I know that A is 1,100 feet. All right. So will you agree with me? Let me write it first. So this is the standard equation of a hyperbola, and we also know that c squared is equal to a squared plus b squared. Will you now agree with me that if I have c and I have a, then I can find b? All right, so let's do that right now. So c squared, so c is 2,640. squared will equal A, which is 1100 squared, plus B squared. All right. Now I'm going to go ahead and just solve this. So in this case, B squared. All right, I'm going to go ahead and write. So I'm going to go ahead and write all this out. So in this case, B squared would be 5,759,000. Gosh, I can't read my handwriting. I don't know if that's 600 or 500. Let me see if I can find it on another page. No, yeah, it's 600, I think. All right. So I almost got my equation here. So I know what B squared is. Let me go ahead and square out A. So if A is 1100, then A squared is going to be 1,210,000. Okay, so at this point right now, I can construct my equation of the hyperbola that models this explosion. Ready? So we're going to draw a horizontal transverse axis. So we want the A to be the positive and negative, and B will, and because it's under X, and then we want the X to be the positive, so that would mean that A is going under X. So that leaves me with X squared over A squared. So in this case would be X squared over 1,210,000 minus, oh, I'm running out of space. Let's see if I can grab that and move down here. Just way too much clutter. Just too much clutter. Let's try that again. So, all right. So X squared over 1,210,000 minus Y squared over 5,759,600. And that equals 1. All right, so that is the equation of the hyperbola that models this explosion. We know that the right branch is the only one. So if you graph it, this is the graph that you're seeing here, okay? The right branch is the only one we care about. Now, this picture is a little bit misleading. It would make you think that the explosion occurred right here where I'm pointing. But do you understand that at this stage, the only thing that we can say, listen to me, we only have 2 microphones. With 2 microphones, the only thing that we can say is that the explosion occurred somewhere on this branch. Okay? Now, what would we need to actually find out where the explosion occurred? We would need a 3rd microphone. If we have access to a 3rd microphone, it doesn't matter where, you would, this is a little bit hard to draw with a stylus, but you would end up drawing multiple sets of hyperbolas, like 3 sets of hyperbolas, and you would find, I'll do my best, my apologies. So this is going to be a nightmare. Let's say you had 3 microphones, okay? And let's say you had hyperbolas for each. And I'm doing my best here. Well, what would end up happening is, let's see if I can do this one more time. This is an utter failure, I think. Okay. Where, I don't know how this came out with my stylus, but where the intersection between all three branches, where I can't even see if this actually borne out of my drawing, but if there is one part where 3 branches all cross at the same time, at that location, and that's, I don't think I did it very well. I didn't draw very well. So at that location would be the point of the explosion. So anyway, yes, you would need a third microphone to actually figure out where the explosion occurred. But listen, to be able to give a branch, okay, even if it's not an exact location, if it's not an exact longitude and latitude, just to be able to say, to give a set of longitude and latitudes to your commanding officer would be important, right? So anyway, just an application of the hyperbola. We are going to stop this video. This is 10.1. Hopefully it was mostly review. Net 10.2, we're going to go to parametric equations. So again, if you don't have any background in parametric equations, you should brush up on it. I don't do it justice in my videos either, honestly. In the classroom setting, we would have a full hour-and-a-half lecture of parametric equations. I just, unfortunately for the online classes, I rushed through as quickly as I could because of this scenario for the semester. But let me go ahead and conclude, and I'll see you in the next video.